workshop. Yeah. Welcome to all. I'm Olivier Gaudoin. I am a professor of statistics and director of international relations at Grenoble INP NCMAG, the Graduate School of Informatics and Applied Mathematics in UGA. It's my great pleasure to welcome you to this first MIPT-UGA workshop on artificial intelligence. In fact, MIPT and UGA have a long-standing collaboration. It started in physics and biology many years ago, but recently new contacts has been forged in applied mathematics and computer science, thanks to some people who are here today, like Vadim Strijov or Anatoly Yuditsky and Massih-Reza Amini. And since then, we have worked on student exchange agreements. And it was very successful since in the last 4 years, more than 40 students from MIPT have been enrolled in UGA's master's program in applied mathematics and informatics. We also have some students from UGA, only a few, who spent a semester at MIPT. And now all of them have the possibility to obtain a double master degree. So to have both the master degree at MIPT and at UGA. And this is a brand new possibility, and we want to increase the number of students enrolled in this joint program. Of course, in research, some research collaboration exists already between MIPT and UGA, and you will have some illustrations about this cooperation during this 2 days. But now what we want to do is to strengthen this cooperation and take a new step in the cooperation between the UGA and MIPT. And to this aim in UGA, we have a relevant place for that. It's the Multidisciplinary Institute in Artificial Intelligence, MII, and Massih-Reza Amini will say a few words about that. So this workshop aims to increase our mutual knowledge, to generate new contact, and hopefully to start new collaborations. So finally, I would like to thank a lot Anatoly Yuditsky and Radoslav Neyeshev, who had the idea of the workshop, and they have set up the promising program. So that's all for me. Now I wish all of you a fruitful workshop, and I leave the floor to Vadim Strijov.
Olivier, thank you very much. Probably to Massih or to me?
Well, as you want.
Good morning. Okay. Go ahead, Vadim. Go ahead.
Thanks. I just want to say the university like ours are intended and are good not only the teaching activities, but for the scientific activities and social activities. And here we are to do this kind of job, to this kind of activities. And in fact, the younger people we involve in science, the better our quality of research is. So we from the MIPT side present only one PhD work, couple of master student works, and the main part is Bachelor 3 and Bachelor 4 works. Of course, these works carries some ideas, and I hope these ideas will catch the researchers from UGA and from other labs, and will have productive discussion and continue these works together. So thank you.
Okay, so perhaps it's my turn. Good morning, everyone. So I'm Amini. I'm professor at the University Grenoble-Alpes. I want also to thank Anatoly for inviting me here. I think it's a great idea to have this organization showing the collaboration that exists between MIPT and UGA. It's also my pleasure to see again Vadim, so by video conference. So I will just talk about briefly about the Multidisciplinary Institute in AI that we have here in Grenoble. So it's a part of the national program for artificial intelligence, and the French government constituted a network made of a small number of interdisciplinary artificial intelligence institutes that were granted in 2019. So 4 proposals from Grenoble, which is called MII at Grenoble-Alpes. So it's the MII that you see in the website of this workshop. It's Multidisciplinary Institute of Artificial Intelligence. There's another one at Nice Sophia Antipolis, which is called 3IA Côte d'Azur, Paris, Prairie, and Toulouse, Anity. These 4 institutes are labeled for an initial period of 4 years with a minimum funding which will mobilize about 75 million euros. And the aim here is to promote research, education, and links between industry and public organisms that work in AI. So MII, the Multidisciplinary Institute of Artificial Intelligence Grenoble, is structured around 2 main themes: AI for the future and AI for people and the environment. In terms of scientific activities, the axes are divided into specific programs within about more than 20 chairs, so groups of researchers. In terms of education, in 2019, there were about 700 students that took a training in AI in Grenoble, and the aim was to double this number in 4 years, in terms of 4 years. And in 2021, so the estimation is that there were more than 1,200 students, so not far from the objective that had this qualification of AI. So in the education part, there are 2 labels, professional qualification in AI. One is AI core and integration, that corresponds to the exploitable knowledge in the central themes of AI, and AI practice and application, that corresponds to applications of AI in different fields like health or industry 4.0. About the courses in AI that we have in MII. So there are 2 types of courses: short training courses that are up to 3 days, proposed throughout the year mostly for industrials, and long training courses that are based on existing courses in AI that are given in UGA INP international master programs, like Master of Science in Industrial and Applied Mathematics, MCM, or Master of in Informatics at Grenoble, MOSIG. I just want to add one more point. So with the initiative of UGA and INP, there will be hopefully another master, international master, which is a European master in AI, proposed with 4 other European universities. And we hope that MIPT students will also be interested to follow this master. And a final word. So these 2 days are rich in terms of presentations, scientific presentations, different parts, UGA and MIPT students working in AI. So there are also, I think, one a PhD thesis in co-tutel between between UGA and Skoltech, but with a former student from MIPT that also passed through UGA, the program MCM of UGA. It's Alexandra Brushnikova, who will defend her thesis in December 2021. So thank you very much.
Thank you, Massih. So now, Anatoly, can you say a few words and introduce Julien?
Okay, so just to say 2 words, the idea of this conference is just that people communicate. You will see that there are senior talks, there are very few senior talks, and most of the talks are by young researchers. And actually, they are short. So there will not be much time for questions, but all the information will be available on the website of the event, so you can contact people and ask questions, so don't hesitate to do this. Okay, this is the idea of this workshop, that young people communicate. All right, so that's it, and I would like to introduce right now Julien Mairal. He will be our first senior talk, and he will talk about the reconstruction of high-resolution images from a bunch of raw low-resolution images. Thank you. Okay, I believe that Julien can share his screen right now.
Hello, thank you, Anatoly, for the introduction. Let me try sharing the screen. Okay, so you should be able to see it. I changed a bit the title, but that's the right deck of slides.
Okay, we see it's fine.
Okay,
Anatoly,
well,
sorry,
yeah.
could you say how we could ask questions to Julien? Julien, during your talk or after your talk, please.
So I suggest you can ask. So you can probably ask questions on the chat. Let me see if I can see the chat during my presentation. Anyway, the presentation has 2 parts. So at some point, I will simply stop and see, see if there are questions about the presentation.
Okay, thank you.
I see, but I see. Yeah, I have access to the chat window during my presentation, so don't hesitate to. Yes.
Okay, Julien, if you don't see questions, so maybe when you will stop in the middle of the presentation, I can resume questions in the chat.
Yeah, you can also stop me, and that would be fine. Okay.
All right.
Mm-hmm. Thank you.
Okay, so should I start? Are we good?
Yes, please.
Okay, well, so thanks a lot for the organizers of this this workshop. We enjoyed a lot in the past having MIPT students in our lab. And so this presentation today is about several inverse imaging problems. So the title I gave was a bit restrictive. So here I'm going to present something a bit more general. But I'm going to, first I need to acknowledge my collaborators on this project. So what I'm going to present is also mostly the work of my PhD student, Bruno Lecoua, who is co-advised with Jean Ponce from INRIA Paris. And so the first part of this presentation is actually the one I gave, which is on the website. It's there are several titles for this. The one title I like is called Aliasing is your ally. So end-to-end super resolution from raw image burst. So the goal is to reconstruct high resolution images from a burst of low resolution images that you can acquire with a smartphone or a digital camera. And if you don't know exactly what aliasing is, I'm going to introduce it a bit, but aliasing is typically something that we don't like in image processing. But it turns out that in very specific cases, this is actually a phenomenon which is extremely useful. The other title is called the Lucas-Kanade Reloaded. It's simply because the Lucas-Kanade algorithm is an algorithm which is extremely famous in computer vision. It's an algorithm which was invented for aligning images, and it's an algorithm which is pretty old. It was invented about 40 years ago. And for a long time, it was probably one of the only, computer vision algorithm that was actually working in the wild with real data. So I'm exaggerating a tiny bit, but it's actually something which has been extremely successful. And so, of course, these days in computer vision, people tend to forget about these old algorithms because everybody is using deep neural network. In this presentation, we're going to use as well deep neural network as well as more classical algorithms like this one. So we will advocate hybrid approaches between the deep learning world and a world which is, let's say, formulated in terms of optimization problem that try to take into account the data acquisition process. So let us, start like in experimental sciences. We often start with results. So I will do the same, and that will be also the opportunity to discuss a bit the problem that we want to address. So here, let us consider, for example, this picture. So this is a picture with 20 millions of pixels that was taken using a digital camera. It was a Panasonic camera. And our goal is, given this scene, we want to be able to zoom on these small parts, that are with different colors here. So what you don't see at the moment is that if I simply zoom, on this picture, you see something which is not very good in terms of quality. And the reason of that is that this picture was taken with a very low exposure time, with a high sensitivity for the sensor. So that means that when you have a low exposure time, you don't receive much light, and you have to amplify the signal to reconstruct your image. And when you amplify the signal, you also amplify the noise. So in fact, for this picture, I get a quality which is not very good because I need to amplify the noise. And this is here this is basically the output of the camera. It's not a bad one. It's a, I don't know, a Panasonic camera, which cost about €1,000. Nevertheless, in this high ISO setting, this is what I get. So I hope that the quality of the zoom connection is good enough such that you see that there are lots of artifacts. Now, this was taken with a single, this is what you obtain if you simply zoom on a single picture. But in fact, if instead I take a burst, so basically I simply press the shutter for a long time and it will take a sequence of images. So the camera is, this is here real data. This is a picture I took myself. So if you take a burst of 30 images, so the camera is not on a tripod, I'm simply taking the picture by hand. If I do enough processing for these 30 images, this is the types of results that we're able to obtain on the right. Basically, our goal is to process the raw data from the sensor of the camera of a burst of images and both remove the noise and increase the resolution. So here we try to increase the resolution by 4 on the right. And as we see, there are lots of details that you really don't see when you simply look at the output of the camera. So let us look at a different part of the picture. So this is another part of the picture where, again, you can see the hair that is well reconstructed. And even there are parts of the picture on the left which are overexposed, where it seems that we lose information. In fact, if you do the right processing, you can recover lots of details. I don't know if there is maybe a small lag. You're supposed to see a different picture here. Can you see Elsa here at this point or not yet? I'm waiting a bit because I'm... can you still hear me? Yes?
Yes,
it's
sure.
okay, right? Yeah.
Yes, okay.
Okay, now I think you see the picture I was commenting. Okay. There was probably a small lag. So here, so this person is called Elsa. It's from a Disney movie, and we can recover. It's an interesting picture because there are very high frequency details in the picture that are completely lost in the output of the camera if you take a single image. And if you take a burst of images, you recover lots of things. The last example is something that maybe I should not use for scientific presentations. I should probably not advocate the use of alcohol for that. So you are going to see the picture coming soon. It's just a bottle of rum, but from an image processing point of view, it's also a very interesting picture because there is lots of tiny details that are hard to recover. So I see something, a comment on the chat. Let me open it. Yes, the problem is some now that do not know who is Elsa. So if you were, let's say, 6 years old, probably you would know who is Elsa, but apparently we are a bit older than that. So indeed, the movie is called Frozen, and this is the main character of the movie. And my daughter is 7 years old, so she knows very well who is Elsa. So that was previously the picture was for children. So now we have the picture for more advanced people. So this bottle of rum, you see that there is some text that you cannot just read on the left, and on the right, we can recover even the tiny fonts. So I start with these results because I mean, this is the types of results we like when we do image processing, because very often we work with synthetic data. Here we work with real data. We obtain, I mean, it's not very often that, you know, we obtain this sort of results with real data. So that's why I like to start with that. Now let's discuss briefly the problem. So the problem is, given a set of low resolution frames, which are on the left, we want to reconstruct a high resolution image. And I will simply discuss something which is not very technical, but which is important to understand, which is that the problem is very different from increasing the resolution from a single image. Okay. Why? Because if you try to increase the resolution from a single image, the problem is very ill-posed, and the goal is basically to invent new information, to hallucinate high frequencies. For example, on the right, this is a picture taken from a paper by Google, which was, trying to increase the resolution of faces. So given 8x8 pictures, they were creating samples of 32 pictures of people. So of course, if you do that, there is no way you are going to recover the ground truth. And in fact, you are just going to, in the best case, what you are going to do is to invent faces that look fine. For example, if we take the first row, the generated person in the middle is very different from the ground truth, but it looks realistic and people may be happy about it. Something which is important also to mention is that if you are going to invent details that do not necessarily correspond to the ground truth, you are going to rely on data. So it will be a data-driven approach. And this previous paper from Google, well, people talked a lot about it on Twitter for the following reason. If you see here, people try to apply this, let's say on the low resolution picture of Obama, and it will turn Obama into a white guy, simply because there was a strong bias in the data for this specific example that will simply, turn Obama into a white guy, which obviously is a bad thing. Now, if you have multiple frames, going from a low resolution to high resolution, if your frames are not perfectly well aligned, it turns out that the true information is perhaps present in the data. So the goal is to exploit these image misalignments to artificially increase the number of samples from the underlying signal. So our goal is not really to invent new information. Our goal is to recover information that exists. For example, here we do here a synthetic experiment where we have some ground truth image on the right, and in this synthetic experiment, so again it's synthetic, so it's not perfectly realistic, but we'll generate a burst of it was 20 low resolution images where we generate random affine movements. So what is an affine movement? It's simply a transformation of coordinates, which is an affine transformation. And if you do something like this, well, we can recover the picture that are in the middle. So it's not as sharp as the ground truth on the right, But we can, if we look at the first row, we obtain something which is pretty convincing. Anyway, this is realistic. I prefer the results I presented at the beginning because it was applied on real data. Now, there are a few other things that are important to know from a, let's say, technology point of view. If you don't know how a digital camera works, there is a simplified view that already gives some information, which is that the first important thing to know is that when you create a color image with your camera or with your smartphone, in fact, you don't have the full color information, which is acquired by the sensor. In front of the sensor, for every pixel, we in fact capture a single value. And because there will be colored filters in front of every pixel, what you get is only partial color information. So this partial color information is organized as a pattern, which is called here the Bayer pattern. For example, on the first row, we will acquire green, red, green, red, green, red values, and the other rows will capture green and blue values. So that's what, and so the raw data is actually the output of the acquisition, the number of photons that hits each pixel on a specific color channel. After that, there are a few steps. Probably you want to remove the noise at this point. And then the task of reconstructing the color image is this consists of solving this inverse problem, which is to reconstruct the full color image with 3 values per pixel, given this partial information, which is given by the Bayer pattern. And this task is called demosaicing. And there is a first idea which is important, which is that if you want to process data from your camera, especially if you want to do this multi-frame super resolution task, actually working with the raw data is important. Why? Because we have seen in the first result I showed that if you are manipulating the output of the camera, which is after denoising, after demosaicing, then it turns out that the camera processor is going to produce, to lose lots of information. So I'm not claiming that it's going to do a bad job, but given a single noisy raw image, it will create an image which loses lots of details. This is what we have seen in the previous examples. If you remember the bottle of rum, the text was impossible to read. So first idea, work with raw data, it's important. The second interesting idea is the fact that with the raw data, you can leverage what is called aliasing. So I'm waiting a tiny bit because I think there is again a small lag. And okay, I'm waiting for the lag to finish. And okay, now you should see a picture on the right, an image which is actually moving with lots of artifacts. And on the yes, you don't see it yet.
We don't see it yet.
So we are going to have to wait. Perhaps it's because of my internet connection, which is not fast enough. Okay, now you see it, right?
Yes, it's okay.
Yes.
Okay, good.
Sinus.
So okay, so actually it's better like that. I prefer you to have the high quality image using Zoom, but with a lag. That's better than having lots of details that are lost. Okay, so what is aliasing? Aliasing is a basic phenomenon, which is that if you have a high frequency signal, let's say this red sinusoid here, and you undersample it simply because your sensor has a specific resolution, what you are going to see is something which is different from this high frequency signal. You are going to see low frequency artifacts. So I call that an artifact because the blue low frequency curve actually does not exist in the original signal. It's just something that you see. And on the right, you are supposed to see a picture which was taken using a smartphone. So we took the picture ourselves, and you should see lots of, let's say, orange or bluish artifacts. And clearly these are, you see that the grid has very high frequencies on the right, and the artifacts that you see are just due to this aliasing phenomenon. So typically in image processing, aliasing is bad. Given a single image, it's actually very hard for your algorithm to understand that these artifacts are not present in the original signal. So that's why aliasing is considered to be bad. And typically in front of many cameras, there is even a small low pass filter in front of the sensor. And for us, it's actually something which is pretty bad because, you know, we want to do super resolution, meaning recovering high frequency information. Many cameras have a filter that blur the image before it will reach the sensor. I'm not saying that what we do here will not work with these images. It's just that this anti-aliasing filter will sometimes hurt the quality of the results. But it turns out there are also more and more cameras which do not have this anti-aliasing filter. For example, the camera I used for the results that I showed at the beginning does not have this anti-aliasing filter. So now, why aliasing can be good for multi-frame super resolution? It's simply because the fact that we have lots of samples using these artifacts, in fact, we can, there are ways to remove it. And it's something which is actually known from in the signal processing literature for people working on super resolution. It's actually known that, well known that aliasing is good in this particular setting. So our goal is going to be to exploit images that may have aliasing artifacts, and we want to recover high frequencies from them. Next, another example, there is a tiny lag again, but that's okay. I'm going to start commenting on it. So in the next picture, I'm simply going to give another example to explain why the problem is hard. The problem is hard because for several reasons. Because first, we are going to work with raw data, which is not always not that easy. We are going to take picture by hand with unknown camera motion, which is, it's a small motion, but it is unknown. So the first task will be to accurately align images with subpixel accuracy. Then we will need to deal with the noise which is present in the data. So again, here on the bottom left, you should see the example of noise that we get. And we need to solve this inverse problem, which is the demosaicing task. And in terms of prior work, this multi-frame super resolution problem is actually pretty old. So there are works that were published about 20 years ago on the topic. Probably not with raw data at that time, but there were already interesting algorithms that were addressing this task. For example, here there is a famous paper by Baker and Kanade. On the left, I think they were exploiting 4 low-resolution input images on the left, and what they reconstructed was the green column, the second column, which is already pretty good. At that time, they were assuming the alignment, the movement between the frames to be known, and that was using synthetic data. But that was already something, a class of algorithm that was very interesting for us. There are also, and these types of old algorithms were actually revisited more recently. So this is a paper from SIGGRAPH last year here that was using the same types of algorithms, but with real data. And it's actually a paper by Google. So it's probably this is the types of algorithms that were that are now implemented in some smartphones. And you see, especially if you look at the column, this column on the right, the one before that has lots of aliasing, you see that the reconstruction does not have aliasing artifact anymore. Now, these are algorithms that were basically exploiting let's say, the physics of the data acquisition process to solve an inverse problem. But of course, these days, we also like to use data-driven approaches using deep neural networks. And there was this paper from this year to 2021, which also achieves relatively convincing results by using a deep network. Now, of course, if you are going to use a deep network, it means that you need to have training data. And in fact, there is something which is extremely difficult to do here, which is that working with real data, acquiring ground truth real data is impossible in image processing. Basically, it's actually very hard to simply take a sequence of low resolution image using a camera, and at the same time obtaining a high resolution image, which can be perfectly aligned with the low resolution images. So in this work, they exploit synthetic data, which is pretty realistic, and we are going to exploit this as well in our work. So I'm not going to spend lots of time, on this prior work exploration, but there are a few references in the next slide that you are going to see, that you see now. And you feel free to look at these classical references if you're interested in this topic. For us, something which is interesting is that there are synthetic raw data sets. When I say synthetic, it means real images, but the way the low resolution images are obtained from high resolution images is a synthetic process. And it's realistic enough to obtain good results using these data-driven approaches. Okay, so let us go a bit more into technical details. So I was saying there are let's call it the old world of a classical inverse problem. So what we do when you have an inverse problem is that you write an equation that model the process that generates your observation, which is yk here, meaning your raw low resolution image from some ground truth high resolution image, which is called X here. So X is a RGB color image of high resolution. We assume that there is a warping operator that will simply take into account the fact that there is a hand motion when we take the picture. It is parameterized by some parameters pk. Then there is a integrator B, a blurring operator that takes into account the fact that we are going to integrate over a pixel area. And then there is this decimation operator, undersampling operator D, that takes into account the fact that we are only considering a few pixels. So it will undersample in the spatial domain, but also in the spectral domain, because we are going to keep a single channel per pixel. And I see there is a question on the chat. The question is, how do we measure the quality of the resolution as we do it in optics? It's a very good question. The quality of resolution can be, I don't know if I'm going to answer correctly the question, but the quality of resolution can be due to the resolution of the sensor, but also to the resolution of the optics. In our case, and this is in fact something we observe with real data, we assume that the quality of resolution is only due to the sensor, is mostly due to the sensor. And it's actually something which is, you will see real results with different smartphones. It's something which seems to be true if you want to increase the resolution by a factor 2 or a tiny bit more. Of course, if you wanted to increase the resolution by much more, probably then the optics will be one of the limits. For example, we tried this on astronomical images. The results are not convincing yet because we have to take into account the optics, and there is lots of additional work that is required to make this work, for example, on astronomical images. But if you simply take even a high quality camera like we have here, then in fact, the sensor is already a limitation. And there was a question about what kind of neural networks should we use. I'm going to give some details about this later, I think. Do I have a slide about it? Okay, probably I don't have a slide about it, but okay, let's say the types of neural networks that are used for increasing the resolution. Basically, they correspond to what are called these U-net networks that takes as input an image. It will create a sequence of feature maps whose resolution decreases before it increases up to the resolution you want to obtain as an output. And then there are also details about things that are called a skipped connection. It's a bit hard to explain like this, and it's basically the result of lots of empirical work to design these networks. And I'm going to comment about the limitations of the deep learning model, by the way. So here, that was by the way, what we call the old work of classical inverse problems. So what we do now is that given observations, which are, let's say, a burst of images, y1 to yk, we have a cost function that simply corresponds to the way the data is generated given a ground truth image. This is still often ill-posed, so we have to add a prior for natural images that we call that the function phi theta of x on the right. That can be, for example, the total variation prior. You know, if we take a classical one for natural images, and then we optimize. So then there are many ways to optimize this, and it turns out that there is one which appears in the computer vision literature, which is called half quadratic splitting. It's something that typically, as optimization people, we don't really like. But there is a good reason why it will be useful for us. So people call that half quadratic splitting. It's actually very simple. It's simply an observation that, well, when we look at the objective function, the terms on the left, we know how to minimize it. Let us assume that we know how to compute what is called the proximal operator of the prior phi theta. The idea of half quadratic splitting is simply a penalty. It's called a penalty method also, a quadratic penalty method that consists of introducing an auxiliary variable z. You add a term that encourages z to be close to x. With this scalar parameter mu t, you are going to have mu t that increases along the iterations. And when you see an objective function like this, well, you can simply alternate between the optimization between x, z, and pk. Okay, so let us look at each problem, maybe on the next slide. If we have this cost function that now decouples, have these quadratic terms that encourages z to be close to x, if I fix a z and I minimize with respect to x, it corresponds to computing what is called the proximal operator of the function phi theta. If you fix x and you minimize with respect to z, it's basically a quadratic function. So obviously what you would like to do is simply, for example, a conjugate gradient method. That's something that would be classical. In your case, we will consider very basic gradient descent steps. That will also work. It may be more costly, but it will be very simple. And we need a form of simplicity in the rest of this presentation. And now the other interesting part is that if you fix z and x, and you try to optimize with respect to the affine transformation of coordinates, that will simply here align your image z with your observation yk. Then it turns out that the most famous algorithm to do that is called the Lucas-Kanade algorithm, which was invented in 1981 and which has been extremely successful in computer vision. So it's simply what is the Lucas-Kanade algorithm? It's the combination of a Gauss-Newton algorithm to optimize with respect to the parameters pk. So again, just to clarify, if you are not familiar with that, an affine transformation of coordinates is simply 6 parameters. So basically, we assume that the hand motion that we do can be well approximated by an affine transformation. It's something which is not a good approximation globally, but since we are going to work on small crops of the image, let's say 300 times 300 pixels, it's actually a good approximation. So that's something that we do here. And so I was saying Lucas-Kanade is Gauss-Newton to optimize a cost function like this with respect to pk, plus lots of heuristics that make it pretty robust in the real life. So today we like to use deep neural networks because there have been a huge engineering effort, to make it accessible. We have lots of very nice open source frameworks that work pretty well. But in the past, there was a lot of engineering work that was done to make the Lucas-Kanade algorithm robust. So we are going to benefit from that as well. So here, this is still the old world approach, by the way. It's not, our work, it's the old classical approaches. So the advantage of the old classical approach is that it is pretty robust.
Julien, we don't hear you. So
you cannot. Okay, can you hear me now? Yes, no?
Yes,
Yes,
a bit
again.
of delay, but it's okay, I guess.
Okay, sorry. Yeah, I should have chosen a different place for the connection, but okay. So I was saying that this old world of classical inverse problems has some advantages, which is the robustness to real data. It's also interpretable, meaning it will solve what it is supposed to solve, even so there is some non-convexity here, which is due to the parameter pk. Actually, it's something that works pretty well in practice. Now, the main drawback is that designing a good image prior by hand, it's actually very hard, which leads us to the new world of deep learning models. I should say new and old world of deep learning models, because deep learning models are also pretty old. But in this new world, we are going to encode a form of prior knowledge in different parts of the network. One is in the model architecture. For example, if you use a convolutional neural network for images, you assume that there is some local stationarity in the signal at different scales. It will also give us the ability to train the model parameters end-to-end if you have training data. So it requires to have training data, meaning pairs of low resolution images and high resolution ones. What is nice is that it's often after you work a lot on a specific model, very often you obtain state-of-the-art results. One of the drawbacks is that what you obtain may be also tuned to a specific data distribution. So what will happen if you apply a deep model on a type of images which is very different from the training images? I mean, you don't know what is going to happen. But it's something that we need to, which is also very appealing, because very often you obtain amazing results with these types of models. Okay, what else? Now let us bridge the 2 points of views together with this concept, which I call the trainable algorithms. So there are two ideas that we are going to use. The first one is an idea called plug-and-play priors, which was introduced a few years ago in signal processing. And the idea is that, if you want to design a prior phi theta, which is a function which is supposed to be small if you have a natural image and a high otherwise, there is a simple idea, which is to interpret the proximal operator as a denoising step. So given an input image Z, the proximal operator solves this problem, and you can see it as making an approximation of Z, which is closer to a natural image. So you can see that as a step that removes artifact that is also denoising in some way. Now it turns out that it's very hard to design a function phi theta that has this property, but it turns out we also know very well how to design functions that denoise and that remove artifacts. For example, given training data, we can use a convolutional neural network. So the first idea is that when you have optimization problems like this, simply replace the proximal operator by a convnet that you are going to train using training data. So the idea may look a bit, there are two reasons why it's not a crazy idea. The first point is that in terms of interpretation of the proximal operator as a denoiser, this is consistent with what convolutional neural network is able to do. And the other thing is that if you look at many algorithms, if you look at the convergence proof of these algorithms, very often the only thing that we require is the proximal operator to be non-expansive. And it turns out that this is something we can do using convnet. We can also constrain the weights of the network such that the resulting convnet is also non-expansive. It does not, I'm not claiming it will justify completely this approach, but in terms of convergence of algorithms, you can obtain something using these approaches. The second idea is the idea of unrolled optimization. It's something which is pretty interesting, which consists of considering an optimization procedure, let's say gradient descent, with these steps. So gradient descent with t steps produces an estimate. Let's say we call this x hat of t given input data. The idea is simply to see this sequence of steps as a sequence of operations that may be differentiable. And after you do that, if you adopt this point of view, then you can also start optimizing parameters of a model given training data. For example, you may consider a cost function like this one on the bottom. So we have pairs of high resolution images xi, burst of low resolution images yi, and you may want to optimize your model parameters such that your output of the optimization method is close to the ground truth. In fact, this is something we are going to do. We are going to take this inverse problem point of view that we adopted before based on optimization. So this block, okay. Maybe if I, let me see if I can do something. Is it a question of a lag or maybe simply, I will simply stop.
We hear you when we're talking.
In
Yes.
fact, I hear clearly.
Okay, so
Without
it's
any
maybe
lags.
your fault, Anatoly, no?
Okay,
I don't know.
Maybe it's my problem. Sorry.
No, but maybe not. It's true that probably I should. Anyway, I cannot do anything about it right now, so I'll do my best. Don't hesitate to interrupt me if you need it. So what I was saying is that what we do here is that we adopt this inverse problem point of view, where we derive this block coordinate descent algorithm. We are going to unroll this optimization procedure and do back propagation through these steps and optimize the cost function, which is the one which is present on the bottom of the screen. And if you are from the younger generation, you may like this sort of, images. It's not something that I usually understand, but you can see basically our procedure as a sequence of steps that are alternating between aligning images, so Lucas-Kanade steps, denoising using a CNN, and minimizing the quadratic function with respect to z, which we called max likelihood step. We could give it a different name anyway. And at the end, what we have is that we keep some interpretability for the classical inverse prime formulation. And we also benefit from this data-driven image prior, which is encoded in the CORNET. Let me take the question here. There are two questions. One that I missed before. So how the specific data distribution could be formally described. So that's basic. I think this is one of something which is very complicated for deep networks, because typically, in signal processing, we often like also to put data distribution that we can control. In deep network, the data distribution is simply, samples from the data. So it's very hard to describe, I think, in practice. So even so, we could also try to, there also work to make deep neural networks more robust. So that's not something we adopt here. So the question about the data distribution, I will simply say that as long as we don't try to analyze theoretically what we do, it's very hard to describe the distribution of real data in practice. There are a few things that we can describe. So for example, we can describe pretty well the noise that is produced by digital cameras. So in terms of data distribution, this is a component where we know we know pretty well how to describe. Okay, then there is another question, which is the L2 norm assumes component-wise differences. Yes. How to deal with the fact that images may be misaligned. So let me come back to the formulation, because it's a good question. I need to clarify this. So the formulation is actually, so I have two devices to see the presentation. So I see the lag. So I will know when you will see the equation I want to show. So basically, each time we write, so here you have it. So each time we write the L2 norm on the left, indeed, YK may be misaligned, may not be perfectly aligned with Z, but we have this operator UPK, and UPK is an operator that does also the warping operation. Probably I forgot to introduce this notation. In fact, if you remember in the image formation model, there was blurring, undersampling, and warping. And so this operator UPK does all of this. So that means that indeed, what we want is to optimize PK such that our high resolution image is well aligned with the observations. So probably this is what was missing in my presentation. Okay. So basically the L2 norm makes sense only if you align, indeed. Okay, so now let us look at a few additional results. There is something interesting, which is that given this model, we have experiments with real data. We also did experiments with synthetic data. By synthetic data, I mean you take a high resolution image and you produce a burst of 20 images with random affine motions that we suppose to be unknown when we process the burst. Here, this is a case where we don't add noise and we don't work with raw images for this specific example. We work with RGB images, but we simply look at how far can we go with this approach. And I think we got pretty surprising results. For example, here we try to increase the resolution by 16. So it's really not something realistic in the sense that you will never be able to increase the resolution by 16 using a digital camera. Also because there will be limitations due to optics, and maybe there will be too much mismatch between the true motions and the affine motion model. But if you do synthetic experiments with no noise and random affine motion, this is basically it simply shows that the model is doing what it is supposed to do. For example, here, this is really what you can obtain with 20 images. I think this is also a good example to show that with multiple frames, you can really recover lots of details that are present in the data. I see there was another question at some point. What is the warping UPK in details? So warping is a transformation of okay, yes. It's an affine transformation of coordinates followed by bilinear interpolation. And then after that, you have the undersampling operator. And basically, the Lucas-Kanade algorithm, it's basically optimizing with respect to PK using a Gauss-Newton algorithm. Okay, so here you should see the picture of the market with extreme times 16 super resolution. It's the kind of things that produce very impressive results, even so it's in a setup which is well controlled, where the model corresponds to where the true model corresponds to the model we optimize. But now we can look at additional results with real raw data. So here, this is a picture that we take. So it will appear in a few seconds. We are going to see a picture taken by a smartphone, which is a pixel for a smartphone, where we take a burst of maybe 20 images here. On the left, you are going to see, and now you see the output of the smartphone camera. So it looks nice, except that so this is here, we didn't tweak any setting here. Simply take the picture on the straight. If you zoom really hard, on this red square in the middle, you see that by zooming a lot, the quality is not as good as we may expect. And on the right, this is the output of the processing of a burst of 20 images. And again, here the smartphone was simply taken by hand. Here, this is the one I like. So this is a picture again using the same smartphone. It will appear again in a few seconds. So taken with the same smartphone, you try to zoom on a very tiny detail. And on this tiny detail, you will see very high frequencies. There are also a grid at some point, and you will see demosaicing artifacts, meaning aliasing artifacts. Here we go. You should be able to see it. In the middle, this is what we call the camera ISP. It simply means the output of the camera. ISP is for image, signal processing. I don't remember exactly what it is for. Maybe image signal processing processor or something like that. And on the right, this is what we obtain using a ×4 super resolution. We also try to see if your method was robust with respect to the device. So I have showed you results using a Panasonic camera at the beginning, but we have also results with this Pixel 4a smartphone. We tried with a Samsung S7. So this is another picture taken while we are simply zoom on a very tiny part. And here, I mean, something that we cannot read, suddenly you can read it. The next result is with the Panasonic camera. It's taken in my place. And again, this is let us wait a few seconds. Again, these are pictures where we cannot see the text in the middle, and after processing the burst, we see it. We have also quantitative experiments. So quantitative experiments, it's actually difficult because with real data, it's often impossible to do real quantitative evaluation. So here, what we use is, and it will be also the good opportunity to tell you as well where the data comes from. So the data comes from this paper, Bat et al. 2021, which introduces a data set of quite realistic raw burst of images given a high resolution color image. So even if the data set is generated using synthetic motion and synthetic noise, we are going to train on these data sets. And this is the models that we have, the results that I've showed you on real data were trained using the synthetic raw data sets. And we believe that one of the advantages of adopting this hybrid point of view between the inverse problem and the deep network is allowing to obtain models that are pretty robust. Basically, you train on synthetic data and you obtain good results on real data. So here the evaluation is on synthetic data, because this is the only setup where we can really evaluate the different methods. So what we compare here is in terms of PSNR, we compare to this previous work, this Bat et al. Paper. We obtain the results that are significantly better than them. And something interesting is that we also look at what happens if, let's say we do only single image super resolution using a deep network. And here we obtain this PSNR of 36. And what we can obtain if we apply the multi-frame method is the PSNR slightly greater than 41. So our model assumes that we don't know the motion at test time. So using this synthetic model, we can also evaluate the quality of the alignment we produce. And the quality of the alignment is under 1 pixel. There is a measure of, of a geometric alignment, which is here 0.3 pixels for this task. So we also look at what would happen if we knew the motion. If we knew the motion, we will do a bit better, which is this PSNR of 42. But of course, this will not be realistic because it will assume that the motion is known. What else can we say? Yes, so we can also discuss the issues that we have about the method. So the current limitations, there are two of them. One of them is that we assume the scene to be sharp and static. So by sharp, it means so you should be able to you should be able to see a few failure cases. I will discuss them in details. So by sharp scene, it means that we take pictures often with low exposure time because we prefer to have noise but a sharp image. We don't want to have motion blur in the image. This is something that we'd like to address in the future to model as well some motion blur, but at this point, we assume the scene to be static. And when we say the scene is sharp, it means we assume that the scene may be sharp enough such that it has aliasing. And so it turns out that on digital cameras, there is some aliasing in the picture that you get. This is also why we managed to obtain this sort of results. But it also means that if you are with specific data where the limitation of the resolution is due to optics, our model is not going to be able at this point to process this data. So here we have examples of scenes where there is some motion. For example, here there are some people moving. And what you see is clearly some artifacts. So you should be able to see, for example, let us look at the pictures on the bottom row. We have people moving and we see some ghosting artifacts. And they are due to the fact that we assume the scene to be static. It's not the case. Okay. This is the conclusion for this part, but this will be also the conclusion for my presentation. So there are some take-home messages, which are that 40 years old computer vision algorithms are useful. So here, really, I think the robustness is due to the use of the Lucas-Kanade method. Also, aliasing is good. So if you have, basically, if you buy a camera and at some point you want to do super resolution, well, don't buy a camera that will blur your image before sending the image to the sensor. That's actually bad. The classical approaches from the old, let's say the old world of image, inverse image problems are interpretable, they are robust, but it's also good to help them by using deep learning principles. As future work, like I said, we would like to go beyond static scenes. I mentioned astronomical imaging. In fact, we are working with people from, who are experts in this domain. And we would like to extend the approach where, recovering the true signal is very important. We just don't want to hallucinate details. We want to recover the true signal. And given the fact that we are going to deal with bursts of images, there are plenty of other tasks that we could address, such as, doing panoramas, high dynamic range imaging, and so on. And I will stop here and I will take questions if there are other questions. Let us. So it's, I don't know who say that. It's probably Anatoly. So no, maybe not Anatoly. If I will see you from Grenoble, maybe not. No. If you are at MIPT, no. But we have a plan, simply to take a picture. In Grenoble, there are a few mountains around, and we want to take a picture from Grenoble and generate, an image from Grenoble with 1 billion of pixels by using super resolution. That's something we would like to do. We are just waiting the weather to be good. Actually, it should be possible to do this these days, but yes, we want to generate basically images with billions of pixels to see how far we can do with real data. And I will be happy to answer any additional questions. So really don't hesitate to unmute yourself if you want to ask questions at this point, or simply to use the chat. So if there are no other questions, we are also on time, to move for the next session. I think we are exactly on time.
Actually, can I?
Yes.
Can I ask you a question? So maybe it's a stupid question because this deep neural stuff is completely I have completely no knowledge to this, but in usual inverse problem, how to come the robustness. There are some how to say. Well, as far as I understand, the neural net is the images you have trained your neural net on, it's to some manifold. Then, if the image you get it is not in this manifold, the result can be pretty random. So, in usual linear inverse problem, you basically know how to control the robustness. You use the penalty exactly to control the norm of the operator, of the covering operator. So do you have these things like this with neural nets?
There are a few things we can say. I think one thing we can say is that if you are if you want to increase the robustness of deep networks, there are classical ways that use more or less robust optimization. Basically, you want to minimize your risk, and your prediction function has a max over some ball. And it's something which is actually very useful in many contexts. It's just make the optimization very painful. Very often, also, what we observe is that there is something strange going on, which is that in some recent work, to achieve robustness, you need both this approach using robust optimization, but it turns out that it seems you need more parameters to achieve both robustness and generalization. So it's not something I understand very well, but at least what I could claim is that with these hybrid approaches, where we still have this interpretation in terms of inverse problems, like you say, we could control some norms of operators and achieve the robustness because of that. Now, I will not claim that controlling these norms is something that we have done. We simply use the convnet with the basic regularization that everybody uses. But in principle, we could control, the stability of this optimization process, in a way which I think is much easier to do than if you simply use the deep network as a black box. But probably, it's something we could also discuss maybe in more details one of these days, if I visit you on the campus.
Sure. Thank you. Thank you, Julien.
In fact, I will gladly join your discussion, since I have more tough question than Anatoly has. For the neural networks, the complexity of neural networks grow much more faster than the complexity of the optimization of the target function of the quality criterion. So your quality criterion carries only 2 or 3 parts. Am I right?
Mm-hmm.
Yes. And your neural network is huge. Why don't we act a little bit vice versa? We will grow the complexity of the quality criterion of the target function, including all stuff we need, say stability, complexity, accuracy, etc., and keep the modest, simple structure of the neural network. So to severe the optimization problem for Anatoly.
So the question of the complexity of the neural net, for me, it's a bit hard to understand. There are 2 things I can say that are, I don't know if it will address exactly your question, at least it will relate it to your questions. There are 2 things. One is that in this work, we use convnet, as a denoiser, which is something with many parameters that people use for super resolution. Mm-hmm. And in another part of the talk, which I did not present, I also present models where the hybrid approach is related to some simplicity criterion, which is about sparse estimation. And in this other part of the work, what we obtain is that by using this point of view of inverse problems, we obtain deep networks, networks that have much fewer parameters than what a classical deep networks would have to achieve the same performance. Let's say in some case, we have a factor 10, between 10 and 20 less parameters using these other approaches. So it means that in terms of the complexity of these models that are hybrid and between optimization and deep networks, I don't really know how to explain, the number of parameters. It's maybe not exactly what we need in terms of measure of complexity. Now, the other thing which has nothing to do, I could say, is that I was trying to mention this to Anatoly before, is that there are recent works which I have not read yet, so I should probably not talk too much about it, where it seems that the conclusion is that if you want to have a model which is robust and smooth, that is, that will also be stable in some way, then you need a huge number of parameters. And I mean, the theoretical estimates that were given were that for natural images, you know, even 1 billion of parameters is more or less the order of magnitudes you need if you want to have both guarantees of robustness plus smoothness. Again, it does not, so it gives it simply say that the question is difficult because the conclusion is maybe different. I don't know if it would apply to these hybrid approaches that have optimization inside the forward pass, where it seems that we can achieve robustness with less parameters. So it basically say that I cannot answer clearly your questions because I just don't know exactly the answer. We just have a few breaks, sure, that are present these days.
Thank you. It's not only difficult, it's kind of philosophical. Sorry for that. Okay.
Thank you very much, Julien. So thank you very much, and thank you for the questions. And okay, let us make a break, and we will be back in 10 minutes. So thank you.
Okay.
Thank you. maybe we can wait a few minutes. It's not like the real conference, so we can ring a bell just to call people back. So let's wait 2 minutes before we start. So maybe for student presentations, I suggest that we just don't interrupt and we wait with questions till the end, right? Okay.
Sounds good to me. Do I need hosting permissions?
Normally, Vadim should give you host permissions.
Yes, it's already done.
Thank you. Do I need to record also from Zoom, or is that handled through YouTube?
It is already recorded in YouTube.
Good.
So it goes.
Thank you.
Okay, guys, please collect all the questions in chat or in your mind and ask after. Am I right?
Yes, I think this is the idea. So for seniors, this is easier to control the presentation and answer the question online, but okay. For students, I think it is better just to wait till the end. Thank you.
I see there's still a few people joining, but shall we get started?
Why not?
Hugo, are you all set?
Yes.
Okay. So yeah, welcome back, everyone. We're going to have now 3 talks of 30 minutes in this session, where, as we said, the talks themselves will be 25 minutes, and we'll have about 5 minutes for questions after the talk. So please reserve your questions for that time. And yeah, our first speaker will be Hugo LEBEAU from the GIBS Lab and ENSTA. And he's going to be talking about cost-efficient classification on large dimensional data streaming. Please go ahead, Hugo.
Okay, so thank you. So yes, I'm Hugo from GIBS Lab. I'm currently doing my end of master internship at GIBS Lab, and I'm going to present how random matrix theory can help us do cost-efficient classification. So and I'm working under the supervision of Romain Couillet and Florent Chatelain. So my presentation will be divided in 2 parts. So first, I'm going to present how we can do resource efficient spectral clustering. And then I'm going to present how we can do classification on large dimensional data streaming. So first, let's start with a classical setting where we have our data of dimension P, and we have n samples of data that we put in our data matrix X. We suppose that our data is divided into two classes of center plus and minus mu. And we want to study this setting when the dimension of the data and the number of data goes to infinity. So P and N go to infinity, but they go to infinity at the same speed. So the ratio P over N converges to some constant, some positive constant. So for this, we're going to study the kernel matrix. So it's the standard gram matrix, which is of size n times n. So obviously, as n goes very large, we cannot compute all this matrix because it is too costly. So one idea to reduce the size of this matrix is so instead of computing all the n squared terms, we'll only consider an epsilon portion of the columns of our data matrix and do subsampling and compute the reduced kernel matrix. So if we take some epsilon, we'll have a reduced kernel matrix of size n epsilon times n epsilon. So in this case, what we know is that there is some region where we can do classification and another region where we cannot. So here on the horizontal axis, well, I think this is better this way. On the horizontal axis, you have the value of epsilon. So as epsilon goes lower, the calculus is cheaper. And here is on the vertical axis is the difficulty of the classification. So it's represented by the norm of mu, which is the center of our classes, plus and minus mu. So here we can do classification, and here we cannot with subsampling. Another idea to do a cost-efficient classification is to do kernel puncturing. So instead of doing subsampling here, we'll just apply a mask on the kernel matrix. So this mask is just a matrix B of zeros and one. So this is the pointwise matrix multiplication. This mask B is a matrix of zeros and one, which follows a Bernoulli distribution. Each term is a Bernoulli variable. So what we have in the end is just a punctured kernel matrix. This is a matrix which is very sparse and has only an epsilon portion of elements. And in this case, the region where we can do classification is much larger. And what we see is that we can reduce the number of elements in the matrix. So we can reduce here epsilon for almost free, because here you see the curve is very flat. So it means that we can reduce epsilon without losing performance here. We can do classification for a mu squared around 0.1 and with a 50 times free calculus gain. Okay, so now we can go even further and do puncturing in sample and in kernel. So we are left with this kernel matrix where we have a puncturing S, which is also a Bernoulli mask, on the data matrix X, and we apply a second mask on the Bernoulli on the kernel matrix. So it is well represented by this schematic where we have just the kernel matrix, here the punctured data matrix, and a second mask applied to the kernel matrix. And in this setting, random matrix theory tells us what clustering error. So we have the expression of the asymptotic clustering error. So here Q is the Gaussian tail function. And you see it only depends on this zeta, and zeta is just expressed as with C0, which is the ratio P over N, the norm of mu, which represents the difficulty of the classification, and the two parameters epsilon S and epsilon B, which define our masks S and B. So in this case, if we keep this zeta constant, we see that we'll have the same, roughly the same clustering error. And we can do the same observation for a different value of theta. Okay, so practically how it works, we can represent the eigenvalue distribution. So here is the eigenvalue distribution of the matrix K times B. So K is the kernel matrix and B is the Bernoulli mass that we apply to the kernel matrix. And if we represent the eigenvalue distribution, we have something like this. So in red is what is predicted by the theory. So LSD means limiting spectral distribution. And in blue is what we see. So you see it fits very well with the theory. And we have one spike. So in our case, we have only one spike, which is an isolated eigenvalue, which represents actually the signal that we are interested in. And if we look at this isolated eigenvalue to the eigenvector associated to this isolated eigenvalue, we see that we retrieve the classes, the original classes, and we can do clustering with that. So this can be used to real data. So here it's done on GAN-generated images where we want to distinguish tabby versus collie, so cats versus dogs, basically. And what we see is the same phenomenon as before, as predicted by the theory. We can reduce epsilon for almost free without losing performance. And then after some threshold, the performance, there is this avalanche phenomenon, performance goes very low. And we can do exactly the same thing on a different data set, and the same phenomenon appears. We can reduce for epsilon for almost free, and then there is this avalanche. Okay, so now I'm going to present a slightly different setting, which is useful for classification on data streams. So this is still an ongoing work that I'm doing with Romain Couillet and Florent Chatelain. So we are still considering the same original setting where we have n samples of dimension p, and they are still divided into two classes of centers plus and minus mu. And we study this setting as p and n goes to infinity. So we have the kernel matrix, which looks something like this. And here we now consider that the data come, so at each, we cannot store the data anymore. And at each time step, we see only L samples. And so we have a bandwidth of size L. So what it means is that we apply a Toeplitz mask on the kernel matrix. So we keep only a band. So the matrix T is just a band with ones. Well, it's only ones on the band, and the band is of size 2L minus 1, or radius L. So this is how it works, and in practice we usually use a circulant approximation. So it's roughly the same thing. It's just that you have more data on the corners. This is useful because we precisely know the eigenvalues and eigenvectors of the circulant matrix. Actually, the eigenvectors are just the Fourier basis. So if you remember before, I presented this graph where we have here on the horizontal axis, the sparsity of the kernel matrix, and on the vertical axis, the difficulty of the classification. And you remember that in this region, we cannot do classification, and here we can do. So the blue line is for the Bernoulli mask, and the red line is for the subsampling. So we can add on this plot now the same curve for the case of the Toeplitz mask. Or here it's computed for the circulant mask, but it's actually it gives the same result. And we can compare it also with the curve where we can do subsampling, but we take only L columns. So it's the case where we would do classification at each time step. If we consider at each time step the L samples that we have and do classification on these samples, we would have the orange curve. So here, by doing this with the Toeplitz mask, we have a larger region where classification is possible. So you remember also before I presented this graph where we have the eigenvalue distribution, in red the curve that is predicted by the theory, and here the spike, the isolated eigenvalue. And if we look at the eigenvector associated to this eigenvalue, we retrieve the classes, the original classes. In our setting, with the topless mask, it's a bit different. We no longer have only one spike, we have many spikes. And these spikes are distributed in an unfamiliar way. So here we don't really see them very clearly, but believe me, they're here. So there are several spikes. I don't know how many there are here. And if we look at the eigenvector associated to the first spike, here's what we see. So in green is the eigenvector associated to the topless matrix. So it's the theoretical topless eigenvector. So we say that we retrieve the basis associated to the top. And if we look at the second eigenvector, we see the same thing for the second eigenvector of the topless matrix. And it goes on like this for eigenvector 3, 4, 5, and so on. So here we see that we have information in all the eigenvectors. So in order to do classification, we can use this information and try to deconvolve the Fourier basis. I'm saying Fourier between quotes because it's not really a Fourier basis. It's, it would be a Fourier basis for a second matrix, but it's slightly different one for the topless matrix. And what we do is to maximize the projection of the true. So here, consider that D is just a vector of plus and minus 1. And U is the eigenvector of the topless matrix, the true eigenvectors. And we want to maximize the projection of these eigenvectors to the eigenspace spanned by the empirical eigenvectors. So by doing this, we can retrieve the classes plus and minus 1D. And if we do so, we retrieve something like we had in the Bernoulli case. But actually, some very recent results may, I will say this a bit later. So here we can have the asymptotic classification error predicted by the theory, which is in the case where we would use only the first spike. So it means we would only use this eigenvector and say this is class 1, this is class 2. The classification error we would have would be this one, and if we compare with the practice, it actually fits very well with the theory. And we would think now that if we use more eigenvectors, we would have a better performance. But in fact, here I used several visible spikes, and what we see is that we don't really have a better performance, and so we may have to work on the weights that are in our minimization. But some recent results tells us that it may be that just all the information is actually already in the first eigenvectors. So stay tuned if you want to know more about this. So I'll have a few concluding remarks. So we were studying a performance versus cost trade-off. In the case of the kernel puncturing, we've seen that we can have an almost free cost reduction without performance loss. And in the case of data streams, we see that we have a better performance than if we would do only subsampling. Well, I mean, classification on each time step. And we know precisely the shape of the phase transition, so it can help us to tune our parameters for the problem we're trying to solve. And in spectral clustering, we've seen a new behavior in spike models where we have multiple. One question that also remains is how is the circumference approximation close to the topless case? Because we see in practice that the results we have with the circumference approximation fit very well with the topless case, but we still have to confirm this. And all of this paves the way towards a better use of our computing power. We're trying to do high energy savings, not spend too much energy on useless computations, but we still want to keep a high performance. Thank you very much for your attention, and I'll be happy to answer your questions.
Thank you, Hugo. So there are a few questions on the chat already. First of all, how must we read plus or minus mu as a mixture of two normal distributions?
Well, I'm trying to see the chat right now, sorry. So the question is how do we read plus and minus 1, right?
Yeah, so does it mean like a mixture of two normal distributions?
Well, it's just that you have your data is divided into two classes. The first class is of center, it's just a normal distribution of center plus mu. So you can look at this in dimension 1. It would be, for example, if mu is 1, you have one class which is of center 1 distributed around the value 1, and one class which is distributed around the value -1.
And does this apply to real data, or I guess you need to center your data first?
It applies to real data.
Okay. Okay, so the next question, how are I sub p and k related as prior and posterior?
IP and K related. I don't understand the question. IP is the identity matrix. I'm not sure to understand very clearly the question. If you mean this, IP is just the
I'll precise
identity matrix.
this question. So normal distribution with the covariance matrix identity IP. First, why IP? Why identity?
Oh, here it's just for simplicity.
Got for for simplicity.
Yeah.
So
here is for simplicity. We can do the same analysis with the covariance matrix here.
But you can put the K matrix instead of IP. Am I right?
As a covariance?
Yes. Since it is, in fact, as soon as you center the columns of the matrix is, IP could be replaced by the matrix K.
K it could be your empirical. Here it's not, it's the kernel matrix.
Correct.
If you invert the transpose and well, if you put the transpose on the other
estimation
X,
of the matrix I.
Yes, it's
right.
the empirical estimation. But well, here we suppose that IP is the true underlying model.
Mm-hmm. Okay. Thanks.
Next up, we have, shall we try the Hankel matrix after top lists to ease the classification problem?
I don't know what is the Hankel matrix.
In fact, it's kind of a joke since you anyway have a series, some alternatives, right? So CB, this kind of metrics to boost quality of classification, to ease the classification problem. So the Toeplitz matrix, yes, you just use to filter the noise in data. And there are various techniques to filter the noise in data, and why not to try more alternative matrices? That's it.
Oh yeah, we could choose actually the mask we want. Here in the case of data stream, we just choose the Toeplitz matrix. But
okay.
Maybe here I can help answer this question. It's really a matter of application. What you assume is that you collect data for a time duration T, and that L, sorry. So for a time duration L, and these are the only data you can play with. So the inner products you compute in K are the only ones available. So it's not a mask. It's not as if you had the whole thing and you would cut off everything outside the diagonal. You just assume you don't have the luxury of computing anything else but what is on the diagonal, or on the main diagonals. So we don't want to
use the kind of computational complexity by doing that. Right?
No, it's just that in practice, it assumes that the data you collect, you cannot collect more than L data successively. So you can get X1 to XL, but once you get XL plus 1, X1 has to go away because your buffer is too short. So the application we have in mind is something like with weak storage, and we want to proceed to classification on data, even though they are gone away for a long time. So you haven't seen them for a while, but you can still improve their classification. That's what we have in mind. We are not just playing with creating masks for the sake of it. It's just, it's really related to the application. And so the circulant one is just a matter of mathematical tractability, because circulant and toplets are essentially equivalent asymptotically. So, but circulant is not realistic neither, because circulant would assume you have somewhere remembered part of the data, but you don't have this. You really have a toplet structure.
Okay, thank you. And the lower index x1, etc., xn, in fact, it is kind of time or space, not just enumerator in your practical problems.
Yeah, here it would represent times if you want. At each time step, at each time step, we see L data, L samples.
Mm-hmm.
Well, actually, you keep collecting them. It's as if you receive samples from this Gaussian distribution with mean plus or minus mu. So it's like you're seeing images of cats and dogs that go in successively. And based on those so many images you collect, you want the algorithm to identify who is a cat, who is a dog automatically, without even knowing that we are talking about cats and dogs in the first place. It's completely unsupervised. But the funny thing about it, again, is that the cat that you have seen for quite a while ago, you're still able to classify it much further in the future. That's because you have this chaining behavior between all of the data that you kind of keep in mind, in memory, in your process. So we wanted to know, how good this algorithm would perform, and yeah, how the structure would deform the classical spectral clustering algorithm.
Okay. And I guess you answered in this way my last question, why the spikes are so important. You try to enlarge the margin between classes, right?
Yeah, spikes represent the information, actually.
The information in between classes. Yes, this
Yes.
green arrow.
Here would be your information. Here would be your noise, if you want, if you prefer signal over noise.
Mm-hmm.
Yeah, this is something very classical in random matrix theory or in statistical physics. This is what we refer to as phase transition phenomenon. Whenever you have sufficient information or sufficiently powerful information, you will see an eigenvalue popping outside of the rest of the eigenspectrum. And in that case, and only in that case, the eigenvector associated to this eigenvalue is informative. It's related to your population statistics. So here to the vector mu, so here to the classes plus or minus 1. So if ever this eigenvalue gets swallowed inside the main bulk, you lose all the information. This is what Hugo showed you in some of the graphs, where the performance will just dramatically drop at some point.
Yes.
This is where the eigenvalue starts to merge inside and you lose all of the information, at least asymptotically so, when NNP are pretty large.
Mm-hmm. Okay, thank you very much.
Just, may I ask a question? Actually, I was wondering, so if I understand what you want to do is just to do the data compression in a sense. So can you, just like in your image example, can you combine the two approaches, this Bernoulli puncturing and this limited time span? So just in the situation when the images are huge and you can do this random subset of image to combine it to make your computation much easier at the stage when you compute the kernel metrics, right?
Yeah, we could do that. We're not doing it here, but we could merge the two methods. Do a top. Well, we would have a topless mask and a Bernoulli mask. but it would be a sparsification along the flow.
Yeah, the idea is really to say, okay, you have a given buffer size. You cannot collect more data than what is available in your buffer. So do the best of it. So either you collect everything as much as you can and you do everything at once, which we had done in the previous work, or you go with the flow. You keep getting your data, collecting as much as you can and kicking away the oldest ones, but trying still to improve the classification on those you have lost on the way. So these are two aspects. So either real time or just simultaneously. But you have a given buffer size and you do the best out of it. That's what we're trying to do. I'm actually wondering if there's an information theoretical way to write the problem and to know what would be the optimal thing we can do if we have a given buffer size and we want to classify n data of size p. Maybe this can be written information theoretically. We haven't figured that out yet, but this would be an important question, I suppose.
Yeah, so it looks like indeed your curves look like very much that the fixed buffer size guarantees the same accuracy, right? So this classification in possible curve, the blue curve on the picture we see, it was almost the same for two methods.
You mean like the blue and the green?
No, I mean just making the toplets, this toplet truncation, or doing the random sampling, it resulted basically the same performance.
No, it's really the blue versus the green, so you lose. You do lose quite a bit, but that's because it's a different setting. In the
okay, so circulant is blue. Okay.
Yeah, no, circulant is green, which is bad.
Circulant is green. Excuse me. Yes. And
Bernoulli is blue, which is good. The problem is that with the Bernoulli, you assume you have all your data at once. With the circulant, you see them coming on the way. Okay. So it's not really fully comparable in a way.
All right. And what happens, by the way, what happens when n is much smaller than p?
I think
that's you were at the limit when p over n constant, but what happens when p is much larger than n?
Yeah.
Yeah, here it's the opposite. What we showed is 1/100. So if we would go opposite, I don't remember, but it's nasty. It doesn't work as well. Yeah, but it's always the same problem. P much larger than n is a nightmare in the first place. So in that case, I think it makes a whole lot of sense to sparsify inside the matrix X with the the sparsification with the S profile. You reduce effectively the size P. But the problem is that it impacts the SNR. So, well, I don't know. It should. Well, I don't know exactly.
Thank you. Thank you very much.
In the interest of time, I suggest we move on to the next talk. So our next speaker is Waiss Azizian from LGK and ENS. Waiss is going to be talking about expressive power of invariant and equivariant graph neural networks. With that, take it away, Waiss.
Okay. Can you hear me?
Yes.
Okay. First, thank you to the organizers for the invitation, for organizing this workshop. So I'm going to be, presenting the work. So this is a joint work with Mairal, and I'm going to present your work on the expressive power of invariant and equivariant graph neural networks. And this work was presented at ICLEA. Okay, so first, let me introduce you to graph neural networks and invariants and equivariants. So neural networks and graphs. So essentially, the goal is to take graphs as inputs of neural networks models. So in this case, your data set is a set of pairs of graphs and labels, so yi to ym. And the nature of those labels, why, depends on the task at hand. So if you want to do classification or regression, so you want to predict one label per graph. So for instance, one real, and think about just classification of graphs, so protein or molecular classification. But in some contexts, you may also want to output one label for each node of each graph. So if in this case, if your graph has n nodes, your output will be a vector of size n. So yeah, this is what is depicted here. For instance, if you want to do community detection or more generally detect structures on graphs, yeah, you want to output one label for each node of your graph. But the problem when trying to do neural networks on graph is that there are no canonical representation of graphs. So for instance, if you consider this graph here with color as node features, I can choose the labeling of the nodes and then write down its adjacency matrix and put all the features, the node features in a vector. And okay, now I can do a neural networks on this. But actually, if I change the labeling of the nodes, because it's arbitrary, then I get a permuted adjacency matrix and a permuted node vectors. And so, at least in this talk, we will want our models to be to work well with symmetries, more precisely to be equivariant or invariant to this kind of transformation. So to formally state these properties, we need to define the action of a permutation on a vector or a matrix. So for permutation sigma, we define the action of sigma on a vector x by the following equation. So essentially, it's just a permutation sigma applied, which shuffles the coordinates of x, and it's the same for matrix G, except that now you have two indices and sigma is applied to each index. And we retrieve just another notion of graph isomorphism, because if you have two graphs with adjacency matrices G1 and G2, they are isomorphic if and only if there exists a permutation which sends one onto the other. Okay, so now with this definition, we can state the properties that we require our models to have in this talk. So function f will be said to be invariant if any permutation of its input does not change its output. Think about classification or regression, for instance. If you change the representation in your graph, you don't want the class you predicted to change. And a function is said to be equivariant if when you apply a permutation to your input, the same permutation is applied to your output. So think about detection of structure or community detection. If you permute the nodes of your graph, you want the labels you predict to be permuted accordingly. Okay, so now we'll see an example of practical GNN and its limitations in terms of approximation. So the most basic example we can take is our message passing graph neural networks. So they take as input a discrete graph, so with n nodes and initial vectors of node features, for instance, the colors on the nodes that we've seen before. And then the output of this graph neural network is defined inductively, given the vector of node features at layer L. The next vector of node features is obtained with the following formula. So for node I, to compute the next representation of node I, we aggregate all the representation of its neighbors with two functions f1 and f0, and this gives us our new representation for the node I. And typically, f0 and f1 are learnable functions, so they incorporate MLPs or things like this. So you can do learning with this. And you can check that this message passing layer is actually equivariant, so from A shell to A shell plus 1. And so if you add a summation layer or a max pooling layer at the end, you can get an invariant network. Okay, so this will be our basic example. And one of the limitations is that they cannot separate all non-isomorphic graphs. So for instance, if you consider these two graphs with no initial node features, if you take any message passing graph neural network, it will give the same results on both of them. Essentially, if you look at one node, it has two neighbors, and all the nodes are the same. So it's the same situation for every node of the two graphs, and this situation continues across layers. So you get essentially the same result. This simplifies as a consequence for approximation, because if you have a function f, which is approximated by message passing graph neural network, then this implies that on these two graphs, it will give the same result. So since these two graphs are not actually not isomorphic, so they're not a permutation of one another, message passing graph neural network cannot approximate all invariant or equivalent functions. So this simple fact gives us a limitation in terms of approximation. Actually, we can precisely characterize which graph can or cannot be separated by message passing graph neural network using the Weisfeld element test. So this is an approximate isomorphism test for graph. This means that it's an algorithm which tries to determine whether two graphs are isomorphic or not. But since we don't know to do that exactly in polynomial time, you don't get it's not an exact algorithm. So the only guarantee that you get is that if the WL test gives different results on two graphs, G1 and G2, then these two graphs are not isomorphic. But the converse is not true. There are examples of graphs which are not isomorphic and on which the WL test gives the same results. And here is a link with message passing graph neural networks. It has been shown, so by student co-authors, that there exists a message passing graph neural networks which separates two graphs G1 and G2, if and only if the WL test separates them. And as before, this has an important consequence for approximation, because if a function f is approximated by message passing graph neural networks, then this implies that for any two graphs which cannot be distinguished by WL, this function f cannot distinguish them as well. So on the contrary, so this severely limits the approximation power of message passing graph neural networks. So on the contrary, what we would like ideally would be a class of GNN which is universal, which means that we would like a class of GNN which can approximate all invariant or equivalent continuous functions, depending on the task. So we have this kind of guarantees for MLPs. So we would like to have the same for graph neural networks, and that's what existing, at least when this work was done, existing approximation results for GNN focus on. So for instance, relation of pooling or group averaging approaches can be shown to be universal, but to be implemented exactly, you need it requires a lot of, it has a huge complexity. Another line of work has been tensor-based architectures, but to be able to show, to have approximation guarantees, or to be able to show that this class is universal, you will need huge tensors, so tensors over the n, or equivalently objects of size n to the power of n. So this is not these guarantees are not do not apply to practical classes of graph neural network, and that's exactly what we try the questions that we try to answer. What happens when we consider tractable classes of graph neural networks? Can we have approximation guarantees in this case, both in the equivalent and invariant settings, even though the separation power is limited, as we have seen? Okay, so this is our problematic. And now, to answer this question, we will revisit the Stone-Weierstrass theorem for invariant and equivalent functions. So first, let me recall briefly what the Stone-Weierstrass theorem says. So if you have a compact space X, a subalgebra of function f, so by that I mean a set of functions which is a linear space, so stable by addition and multiplication by a scalar, and also stable by pointwise multiplication. And for simplicity, we also assume that the function which is always equal to 1 is in f. Then, if f is this class of functions separates points, that is to say, for any different x and x prime, there exists a function f in this class of function which gives different results on these 2 points, then the closure of f for the uniform norm is a set of all continuous functions. So in other words, I will denote the closure of a class of function this way. In other words, you can approximate any continuous function uniformly with functions in f. But as we have said before, our classes of graphical network do not separate points. So we have to go further. And for this, we will introduce a tool from approximation theory that, as far as I know, has been introduced in this context by Timov. So if you have our class of function f, defined in some set, we associate to f an equivalence relation rho of f, which is defined this way. So x and x prime are said to be equivalent under rho of f, or belong to rho of f, if and only if those 2 points cannot be separated by functions in f. Okay, so intuitively, the smaller this set, the more separating or discriminating your class function is. So formally, if you have 2 sets of functions, f and e, the fact that rho of f included in rho of e means that f is more separating than e, because any 2 points, because this means that any 2 points which cannot be separated by f also cannot be separated by e. Okay, so using this notion, we can reformulate the propositions that we have seen earlier about message passing graph neural networks, which gave an equivalence between the Waiss element test and message passing graph neural networks. So with simple equality, which says that the separating power of message passing graph neural networks is exactly the same as the one of the WA test. Okay, so using this notion, Timov proved the following approximation theorem. So you take you work on a compact space X. You consider a subalgebra of function f. Notice that this time the subalgebra is assumed to it allows function to be vector valued, and which contains the function which is always equal to the vector full of 1. Then the closure of f is described by the following conditions. So to see why they are natural, we take let us take a function small f, which is approximated by a function from capital F, and we see that these conditions are actually immediate for such functions. So if a small function f is approximated by a function from capital F, then it is less discriminating than capital F. Indeed, if there are 2 points which cannot be separated by functions from capital F, then the approximated function small f cannot discriminate them too. And the second condition means that for all x, the f of x is in the closure of the set of images of functions of capital F at this point. So again, this is a natural thing to require, because this is a consequence of pointwise convergence. If small f is approximated by a function from capital F, then this condition is obviously satisfied. So okay, so this inclusion is actually straightforward, and all the hard work needs to be done for the reverse. So Timov showed that there is an equality. So there is equality under the following assumption: that there exists S, a class of real valued function or scalar functions, such that the class of function f is stable under multiplication by the scalar functions S. Okay, so this is not the important condition. The important condition is this one. You also require that S is more separating than f. In other words, you require that there exists a class of scalar functions which summarizes the separating power of your class of vector valued functions. Okay, so first let us apply this theorem in the simple case of real valued functions, because in a case of real valued functions, actually this hypothesis is kind of trivial. In this case, so we get our first we get an answer. This theorem gives us an answer to the first part of our problem. So for real-valued invariant graph neural networks, using the theorem, we actually immediately get that for any almost any class of real graph neural networks, in the invariant case, the set of functions that can be approximated by this class of graph neural networks is exactly the set of functions which is less separating than the class of graph neural networks. And in particular, on the example of message passing graph neural network, as we know what this separating power is for message passing graph neural networks, then we get an explicit description of this class of the approximation capabilities of message passing graph neural networks. Okay, so now we have answered the first part of our question about invariant class of GNNs. And now the question is, can this theorem be applied to equivariant functions? And actually it cannot. So to see this, take a class of equivariant function f and assume that we can somehow satisfy the assumptions of the theorem. So we have a set of scalar function s, which satisfies the two conditions before. So the first condition we said that S satisfies is that capital F is stable under multiplication by capital S. So this means this is the function which is always equal to the vector flow of 1 is in F, and this set of functions is in F. Sorry. But then, since the functions in F are equivariant, this means that all these functions here are equivariant, and this means in turn that all these functions f in S are actually invariant, because an equivariant function with all its coordinates equal means that this means that this function is invariant. Okay, so if we find such S which satisfy this stability property, then this means that the functions in S are invariant. But on the other hand, we would like to require that S is more separating than capital F. So since invariance is encoded in this relation rho, this would imply that the functions in F are actually invariant too. So we cannot apply this theorem to non-trivial cases of equivariant function, and that's where our real contribution starts. Indeed, using equivariance, you can actually relax this assumption, the assumption that there exists a class function S which satisfies rho of S including rho of F. So written with quantifier, this means this to this one. So let us go through the quantifier's version to understand what this means. So the assumption from Timoft requires that there exists a function g in this set of scalar function whenever 2 point x and x prime are separated by a function f. So whenever f of x is different from f of x prime. And actually, what we do is we relax these assumptions to the following. We only require the existence of such a g when not only f of x and f of x prime are different, but their orbits and the action of the permutation group are different, or equivalently when f of x and f of x prime are different in the quotient under Sn. And this can be written compactly this way, which means that S is more separating than the set of functions obtained by composing the functions in F with the projection pi. And so using this assumption, so replacing the original assumption of Timoft with this modified assumption, and now assuming that our functions are equivariant, we can prove a theorem, which an alternate version of Timoft's theorem, which gives exactly the same conclusion, except now with a particular care for the equivalent setting. So this theorem is actually general, so we could put any finite group here. So even though I only presented it for the permutation group, and if we want to focus on the permutation group and on GNN, we can actually simplify the theorem, and in particular simplify those two conditions, which gives us the following result. So it's a result so specifically adapted to the permutation group and the classes of GNN. So if you take still your compact space X, if you take a class F0 of essentially equivalent GNN, so which output a feature for each node of your input graph, which is stable by concatenation, and you consider the class obtained by applying a multilinear perceptron to each of the node features of the output. Then you get this conclusion, which is a simple conclusion we like, which is that the class of function which can be approximated by f is exactly described, is exactly the class of functions which are less separating than your class of GNN. Under this assumption, which is that if you take a function f in f0, then its average over the nodes is still in f0. So you can check these assumptions so if you have an architecture of GNN, you can check whether this function is implemented by your GNN, and if it's not, you can just add a layer at the end, which can only increase expressiveness. So now we can apply. So now we have two results: one for the invariant case, which is a immediate consequence of the results of Timoft, and we have our theorem for the equivalent case. And so in all cases, we can describe the class of functions which are approximated by a class of which can be approximated by the class of GNN. And in particular, in our paper, we apply our results to tensor-based architectures from Maron. And as a bonus, if you know, in particular for these architectures, we know some information about the separating power of your class of GNN, you can combine these approximation results with graph theory to show some, I think, interesting results. For instance, the two-tensor architecture from Maron and these coauthors can actually approximate functions of the spectrum of your matrices if you are on a nice set of matrices. And you also get tensor architectures of order square root of n actually universal and planar graphs, whereas in the general case you need tensors of order n, that's to say objects of size n to the power of n. So to conclude, in this work, we presented a general framework to characterize the approximation capabilities of practical classes of graph neural networks. Yeah, please refer to our paper for the details of the application to GNN architectures. And as a couple of perspectives, what could be interesting would be to extend these results to approximate non-continuous functions. For example, to be able to say to be able to prove that you can approximate angles between eigenvectors of a graph, which can be of interest in graph theory. And ideally, we would also control the number of layers and the intermediate dimension in the GNN used for the approximation. Okay, and thank you for your attention.
Thank you very much, Waiss. Are there questions from the audience? While you're thinking about any questions, I have a few questions. So, yeah, what is it? What do you mean by a planar graph?
By planar graph, I mean graph you can be essentially drawn on the plane without edges crossing.
Okay.
Yeah, so this is a particular class of graph, and yeah, on this particular class of graphs, you can see that you can be universal with less complex architectures.
And what does it mean to be universal?
Oh, sorry. Universal means that you can approximate all invariant or equivalent continuous functions depending on your task.
Got it.
So for standard neural networks, you can approximate all continuous functions, and we would like the same kind of analog results for GNN.
Mm-hmm. Thanks.
Waiss, thank you for the talk. Could you go to the slide number 3, I guess? So,
this one?
Yes, invariant and equivariant functions. You are solving the problem of the graph matching, right? And we no.
Like in this work, I'm only talking about approximation.
Yes, but why do we need the graph approximations?
Like just to have, it's just to have results that are similar to the one on neural networks. Like you can guarantee you can approximate any continuous functions, and we would like to investigate similar results in this context, in the context of graphs as input.
Okay, in this case, we can forget about whether these two graphs are invariant or not. No. The next slide, I guess, number 4. No, number 5.
Okay,
Yes.
no. I'm sorry, can you repeat what the question? Okay.
In the other words, you said that the neural network couldn't approximate these two graphs, right? In fact, it could, but the results will be incorrect.
Yeah.
So you need to transform these two graphs. Am I right or not?
Kind of. Yeah. Well,
What
yeah.
do you mean, kind of?
Sorry. No, what I mean is that whatever the neural networks you take, you will get the same results on these two graphs. Whereas sometimes you don't want to have the same results. For instance, if your application depends on whether your graph is connected or not, you may want your neural networks to understand that they are not connected. That this one is not connected and this one is connected.
Okay.
And so, yeah. And in this case, your GNN would not be able to give you such an information. So it would give you incorrect result if you try to train it for this task.
Okay, I see.
Okay, sorry.
So in fact, after slide, say 7, 8, for me, I don't know, guys, what about you? It was difficult to follow the messages. And the question is, why you don't use some more explicit language, like language of category theory, or say algebraic graph transformations? There are a lot of arrows, pictures to illustrate your research.
Okay, yeah. Thanks for the feedback. I don't know how we could represent these things, using drawings only. Yeah. Okay, because
say like that. I put a useful book. It is the theoretic one, but it presents a convenient way to show the speculations about your math.
Hey, sorry, which book are you talking about?
Look at the chat. Fundamentals of algebraic graph transformations. Okay. The language is a language of category theory.
Okay, thank you. I will take a look.
Thanks.
Yeah, thank you again, Waiss, for the talk. Let's move on to the final talk of the session. So we have Houssam Zenati, who's a PhD student at Invariant and LGK, and also at CRITEO. He's going to be talking about counterfactual learning of stochastic policies with continuous actions. The floor is yours, Houssam.
Thank you, Mintu. Can you hear me well?
Yes.
All right, fine. So I'll be sharing my screen. Okay, can you see it?
Yes.
All right, it's all good. Okay, so hello everyone. My name is Houssam, and I'm currently a second-year PhD student at Invariant and CRITEO under the supervision of Julien. So today I will be talking about one of my first projects here. It's about counterfactual learning of stochastic policies in the case of continuous action. Okay, so I will first of all present the general problem that we're interested in. So in interactive systems such as online recommender or online advertising, full information is not always available, meaning that you actually want to learn to take an action depending on a given situation so as to maximize a reward signal, but you're not sure on what actions you can take and what is the reward of each action. So that is why the full information is not always available. And you want to do this, so to learn how to take actions while ensuring that you're doing a safe and affordable learning. So for example, for drug dosage, you may have some ethical concerns by doing some experiments which are, in the phase of learning with lots of errors and so on, or you may have some financial constraints if you do online advertising. So I will be talking about counterfactual learning and specifically in the case of contextual bandits. So what are offline contextual bandits? So you may be familiar with this, but I will just give a brief reminder. So first of all, the multi-arm bandits is a setup where you have a set of actions, which is finite, and where you want to learn a policy that takes actions to minimize a cost that we call YI, or conversely, to maximize a reward. So cost and reward are just opposites. So a policy, again, is just a function that takes actions, okay? And in the case of contextual bandits, what you're basically doing is you're adding a contextual information on your policy so as to minimize, again, a cost that also depends on the context. So again, you want to learn a policy that depends on actions and context. And in the case of online and offline, the only difference is that in an online learning setup, the policy is deployed. So you're learning sort of an online fashion because signal is observed directly. So you may have this in online learning setups or in the case of A/B testings. And in the offline setting, the cost is actually estimated based on data that was collected on another policy. So you want to estimate the cost for the policy that you're currently optimizing. And the counterfactual learning question is, what would have been the performance of the system should the policy had been slightly different? So counterfactual is basically an offline question. It's an offline learning setup, okay? So now I will be presenting the counterfactual risk minimization setup. So maybe familiar with the empirical risk minimization, which is very standard in machine learning. So counterfactual risk minimization is the basic empirical minimization setup when you do this counterfactual learning, okay? So you're given a context, okay, that is in a context action space, which may be arbitrary, and actions that are sampled from a policy, okay, that you want to evaluate, and you have costs that depend on a distribution that is conditioned on context and actions. And now we will be defining what we call a risk for any policy. That is the expectation of the cost that you have for the context, actions, and the costs that were sampled from the environment, okay? And the way to do this counterfactual question is to basically estimate this risk on samples based from another policy. And how do you do that? It's basically using what we call importance sampling, by actually addressing the distribution mismatch that you have between the policy pi and the policy pi 0 by correcting inside the expectation using this importance weights. And this importance sampling formula actually motivates what we call the inverse propensity scoring estimators, so IPS, which is basically a Monte Carlo estimator of this previous expectation. And the goal of the counterfactual risk minimization now is to find the policy that minimize this empirical risk, and that we also may regularize with, for example, variance penalties or entropy regularization and so on. So this is the general goal and the general objective function that we have in the CRM, so counterfactual risk minimization setup. But this is a hard problem. Why? Because we have a few problems. The first very well-known problem in CRM is the variance problem. So in this illustration, I'm actually illustrating here a policy that we want to evaluate, which is in blue, and the logging policy from which samples of the data set were sampled, okay? And when you actually evaluate a policy that is far from the logging policy in your importance sampling formula, you basically only have a few samples where you can do these estimations. And on those samples, you have that the logging policy here, as you can see in the mass probability, are very low. And this, since those logging policy are actually quite close to zero, you have a lot of variance in your estimation. Again, you also have a problem which is called loss overfitting, which is simply when you have losses costs. When I'm saying losses, it's costs. So the signal yi. So as you can see in this formula, as I said before, if this term is close to zero, then you have lots of variance. And also, if this term is very high for any outlier function, then you may have a lot, what we call loss overfitting. So a few solutions exist for those problems. Is we basically clipped the importance weight and we add some variance penalties in the objective function. Another problem is what we call the equivariant problem. So I'm not sure it's basically the same definition as what Waiss was talking about. But note that if we're interested in cost functions that can be translated, if you take the true expectation and the true definition of the risk of your policy, then you may have this shift, okay, in your cost function. However, if you use the empirical IPS estimator, you do not have this property of equivariance. If you use, however, what we call a self-normalized estimator, by rescaling your IPS estimator with the sum of the importance weights, then you are equivariant, and you also use what we call a multiplicative control variate on this estimator, and this can be proven to have less variance than the original IPS estimator. So to recapitulate, for this two well-known problems, what we can do is, of the variance problem, we do clipped estimators and variance penalties. And for this equivariance properties problem, we actually can use a self-normalized estimator. So now I will be listing the following contributions of our paper. So first of all, we propose a new contextual modeling for the continuous actions case and a regularized estimator. We also focus on the optimization perspectives of the CRM general objective function by introducing what we call a soft clipping and the general use of proximal point algorithms. And we also release a new large-scale real-world data set for continuous actions and propose a new offline evaluation protocol. But this point, I will not give so much detail because of time constraints. Okay, so in the continuous action setup, okay, we again recall that we are considering stochastic parametrized policies for which, as we had in the previous illustration, you may do a simple parametrization of normal policies or even log normal policies if you want. And for those, how do you actually do the contextual modeling? You can do it with a parametrization of the context space, which can be linear, which can be non-linear, or can be piecewise constant with, for example, stratified tree in the feature space. And you may learn a policy that, for example, is a normal distribution, okay, where you have the mean of the policy, which is this contextual modeling that we were talking about. So in our modeling, what we actually did was learning a joint representation on both the context and the actions, as we do in what we call direct methods that model loss predictors in the form of a function, which is the reward function, based on a semi-parametric representation of the context and the actions, where you have here a parameter that is learned on top of a feature map that we will be discussing in the next slide. And for this counterfactual loss predictor, what we will be doing is actually build a stochastic policy that will be a simple normal distribution on top of a prediction that can be the minimizer of this loss predictor that we have defined above. I don't know if it's clear enough, but I hope the next model here will clarify this. Otherwise, please feel free to ask any questions in the question session. So instead of using this general Algerine formulation, we actually propose to use a soft argument operator on the action space so as to make the objective function differentiable with regard to the parameter that we had. And for that, we use M anchor points and on the action space, and we perform an Nystrom approximation on the kernel action feature map. That is the kernel representation that we use for the actions, and then on the context space. So to recapitulate the model and to hopefully make it clearer, recall that we had context, okay, and then actions. Now what we want to do is learn a joint embedding, okay, for this loss predictor eta, and then what we actually perform is a Nystrom approximation in the action space so as to encode the smoothness information in the continuous action space. And then once we have this feature map where we perform the Nystrom approximation, we learn this loss predictor, and then we obtain the policy that we defined before, which is centered around this soft argument mu that we defined here in this formula. Okay. Now, as for the modeling, we also propose a regularization which is more suited for gradient-based optimization. So recall, as I said before, that counterfactual estimators suffer from unbounded invariance. So the classic solution, as I mentioned, was to use clipping of the importance weights. Okay, and the hard clipping that is used in the research literature is the one that you can see here in blue. So imagine that your importance weight, for example, in that illustration goes above the value of 4, then you have this flat optimization landscape, which is problematic. So instead, what we want to use is this green function, which is logarithmic, and which expression here is given, and which gives you a smooth function for which you do not have any stationary points in your optimization landscape, okay? And this is what we call continuous and differentiable operator, and we call it soft clipping. And this is what we use instead of the hard clipping estimator. Also, since the learning problem is non-convex, because of all the regularization that we have, you know, clipping, self-normalized, variance penalty, and so on, we actually tried to use proximal point methods that approximately solve a sequence of sub-problems that are better conditioned than the original the original problem. So the intuition of this proximal point method is this is actually a well-studied algorithm in the machine learning literature, and in the non-convex setup, it basically just makes your problem a bit better conditioned, as I said, and less non-convex, okay? Because you add this quadratic penalty, as I actually have in this illustration, that makes your optimization landscape easier to learn locally, to optimize, sorry, locally. Okay, now going to the evaluation part. So for the evaluation part, I will just present a new dataset that we released from the Criteo company. So it's a dataset that actually has features X, okay? And for those features, you want to learn to take an action and decide which amounts you want to bid for your user. So basically in the Criteo setup, to give maybe a simpler formulation, say you have users that come into a website, okay? Those users have contextual information, and you want to learn whether you want to recommend them this product or another. So you want to take an action that can be to recommend that product or another one. And to learn this recommendation, we in this dataset have encoded the contextual information as features, the amount on which you want to bid them, and also the cost that you have if you do this action. So all those samples are actually drawn from a given policy that we call pi0. This is a logging policy. And as we said, in this setup, we want to learn a better policy for which we want to estimate whether we would have had a better reward if we have taken other actions. I hope it's clear. So we also introduce a synthetic setup, which is easier, to illustrate, and for which we wish to, how do you say, simplify the previous setup actually. So this is what we call a potential prediction setup. So we also mimic the previous setup where we have users in a very toy example, which is a 2D. So this is, for example, noisy moons. So you have users that belong to a group of users. So this is what we would say that group of users which are responsive to your product. This is a group of users which are not responsive. So this responsiveness is modelized with the potentials, okay? And you want to learn to predict the potential of a user given its context, okay? And and so as to better learn this policy. Okay, maybe. I hope it's clear. Otherwise, please feel free to ask any questions. Okay, so we also use a semi-synthetic data in our experiments, which is from the medical, it's a medical treatment data set. And what you only have to know is that we actually simulate a contextual bandit environment by taking the medical experts' therapeutic perspectives and then build a synthetic reward function for which we have a reward if the action that is taken is close to the expert prescription. Okay, then we generate training, validation, and test set for which we perform model selection in an offline evaluation protocol using SNP estimates and discarding policies based on important sampling diagnostics. Okay, so now I will be presenting the experimental section. Okay, so first of all, the first question that we may ask is the continuous modeling necessary in continuous action space, and what do we have if we only actually use discretized strategies? So discretized strategies would actually consist in taking your continuous action space, okay, and then take buckets and learn and using the discrete CRM models that exist in the research literatures. And as you can see in this plot, if you use a number of anchor points, which is very low in the discretized action state, you actually have low performances. Whereas if you use the continuous modeling, even with a few anchor points, you have better performances on these noisy moons datasets. So naive discretization strategies actually prevent you from exploiting smoothness assumptions on your cost function and from exploiting the continuous structure on the action space. Then if you compare the different contextual modelings on all the data sets that we have, so this is, sorry, this is a blank, this is the Criteo data sets. I don't know why it does not appear. You can see that overall our CLP parameterization improves over all the baselines, which basically highlights the effectiveness of the modeling where you take into account both the context action and the action space, and by leveraging the continuous action structure as well. Then as for the soft clipping strategy, we actually give scatter plots here where you can see 3 data sets, and for which you can see the improvement in the test performance when you use the classic clipping compared to the soft clipping. All the points that you see here are different choices of clipping parameters, initializations, hyperparameters that are optimized on the validation set, and also using our offline evaluation protocol. So in conclusion, soft clipping improves over the previous hard clipping. And then as for the proximal point algorithms, again, we have a scatter plot here that compares the base optimizer with the proximal point algorithm. So you can see improvements in your optimization, your test performance. Here you can see that if you compare the loss function with regard to using the proximal point and not using the loss proximal point, we have a better local minima in our experiments using these histograms. And here in that plot, we actually compared the number of proximal iterations. So we were asking ourselves what performance we have if we take more proximal point steps. And we can see that after a given number, at the beginning, the performance improves, but it starts to reach a plateau. And you actually have the same conclusions with different optimizers. So whether it be LBFGS or conjugate gradients. So this is just to give a further discussion on how, what configuration you may use in your proximal point algorithm. And you can see that overall, with different optimizers and with different number of proximal point iterations, you still have an improvement in your test performance. So I guess it was a lot of information, but to recapitulate it, as for the modeling on continuous action space, just keep in mind that it requires more than simple discretization strategies. And our proposed CLP method that takes into account both the continuous the action space and the context space achieves the best results. Then as for the optimization, this is actually an aspect that was overlooked in the research literature in the counterfactual learning community, because all previous papers have been using simple LBFGS optimizer or SGDs. However, if you introduce smooth clipping, you actually have a better optimization landscapes, maybe. And if you use proximal point methods that are known to somehow regularize non-convex learning objectives, then you may have better performances in your serum system. And then as for the evaluation, I did not give lots of details as for the offline protocol, but this is also an interesting question that we may tackle in another talk. And also we provide a new real-world data sets for which we achieve as well good performances with our proposed method. So for future work, we would like to investigate what we call doubly robust estimators with the CLP model. So doubly robust estimators actually take a compromise between IPS, so the counterfactual learning modeling, and what we call direct methods, which learn also a loss predictor and take greedy actions with regard to that loss predictor. So I am done. So if you have any questions, please, or any clarifications that you may want to ask, feel free to ask your questions.
Thank you, Houssam.
Welcome.
There were some questions in the chat.
Okay, let me go back to the chat. I cannot see it.
So the first is ETA could be a neural network, right?
Yes, yes, indeed. Of course, ETA. So as you can see here, again, you have your context and your actions, right? And you have this loss predictor. We took the choice of doing a semi-parametric modeling where you have this feature map representation, and then you learn a linear model on top of it. So definitely you could do directly a neural network for this loss predictor.
And okay, so the second question was, I think, about how the reward was defined in terms of sales and cost.
Yes, thank you for the question. So this was actually a detail on the Criteau data set. So when you have a user that comes into a website, okay, the user has some information, and this is a funny, story, because this actually setup may become a bit more intricate as companies are going into more privacy preserving setups, you know. But let's say from a year ago, what you would have is a user has cookies, okay, and then so this is the contextual information that you have. Then once you have this information, you're going to take to participate to an auction, okay, for which you have lots of advertiser companies, such as Google, Facebook, or Criteau. Then once you bid this, once you participate to that auction, you're going to generate this bid that is going to say to other people in the auction how much you're willing to pay for that user. if that user is high potential or low potential, as I tried to vulgarize in this setup, you're going to bid high or low, okay? So if you win the auction, then you're going to pay a cost because you bidded a certain amount. Then the cost is how you have spent for that user. Then you wish that your amount that you paid is going to generate some sales, okay? That are going to be, for example, if the user has clicked on your product, or if the user has concluded a purchase. And then the general reward function is a combination of the sales minus the, what you have spent, you know. So it's a basic, economic formula that you have between what you have spent and what you have earned.
Mm-hmm. Okay, thanks. I think that answers the question. Are there any questions from the audience?
Yes, I have one.
Yes, Waiss.
Just on the slide about equivariance, you will renormalize your estimator.
Yes.
But as far as I understand, this introduces a bias, isn't it? Or not? Like
indeed. Good point. This estimator actually is biased. However, it is consistent. So asymptotically, you do converge to the right value of your loss of your expected risk. Sorry.
Okay, I see. Thanks.
But this is actually a very common trick, you know, in the importance sampling literature. So apart from the, you know, counterfactual learning community and so on, and all those CRM regularizers and estimators, if you look at the statistical literature, whenever they do this importance sampling trick, they do recommend to renormalize by the importance weight, because it specifically in the cases where your policy is, you know, very far from the policy that you're considering in your logging policy, then you sort of renormalize it and have a better estimate. So again, I could give some more details about it, but not so much time. But in the cases where you do this importance sampling, you know, estimation, it's very common to use that self-normalized estimator. Because if you look at this term, you know, in expectation, it has a value of 1. So if you also redivide it by 1 over n, you know, and you also redivide it by 1 over n on top.
Yeah.
I have maybe a follow-up question. So when or why is equivariance important in practice?
Sorry, 1 second. Houssam ran out of battery, so he will take my place.
I'm very sorry for this problem. So I was just saying that I ran out of battery. So to answer your question, the term below had an expectation of 1. So if you redivide it, it's what we call a multiplicative control variate. And it's also well known in the importance sampling literature. So if you have other questions.
Thank you.
J'aurais dû brancher mon ordi.
Yeah, so I have a related question. So when and why is equivariance important in practice?
So, okay, good question. I will try to answer it very quickly. Say that you have, again, in your Creteo dataset, you have a reward engineering, you have an engineer, you know, which does this reward adjustment, this reward engineering, and he does that in a way that makes some choices, you know, it's a modeling choices. So if your reward is done, for example, negative, then it's a choice of modeling. However, if your optimization solution is not the same, just because you have a translation shift in your reward engineering, then it's something which poses problem, you know. So that's why it's actually an important problem. Just because you translate your reward, you still want to have the same optimization solution.
Thank you. Are there any other questions?
Say, if it is not too late for lunch, I have one small.
Yes.
You have a great line in your conclusions about the continuum space, but instead of studying the topology of this space, the dimensionality, the connectivity, you are studying the statistical properties of the target. So what do you think about this concept, the topology of design space versus statistical properties of the target space?
What do you call, sorry, the target space?
Y, I mean labels.
Okay, so the losses? The cost. The cost, sorry, yes.
Yes. So your main efforts are on the targets.
No, sorry. So the continuous, it's about so you have the context space, and then you also have the action space.
Okay.
And in the general literature, it's the case which was very well studied is the discrete actions case. So as I said before, for example, in the multi-armed bandit, you have only a finite set of actions. So what I was focusing on is a continuous action space, not the space of the target, you know. So the space of target, of course, the space of cost can be continuous, but I was focusing on the continuous action space. Did I miss your question, or is it?
No. It's in fact, it was a very broad question about the topology of the design space. And if it is continuously connected to the target, it is great too.
Yes.
Thanks.
You're welcome.
Since we are over time, I suggest we wrap up. Thank you, Houssam.
Thank you, Mintu.
We'll be back after lunch.
Yes.